Now we will learn the definition of the Laplace transform. So the Laplace transform is basically a way we could solve many differential equations without using the traditional methods to solve these problems. So when we want to use Laplace, we basically use algebra to solve differential equations. When we take the Laplace transform of a function f of t, we get capital F of s. Okay, the input of our function changes, and we get the integral from 0 to infinity of e to the negative st f of t dt. And this is a standard definition of the Laplace transform. So this formula e to the negative st f of t dt is important. We will use these to solve some Laplace transforms, but in the future, what will happen is most of the time you will be provided a Laplace table, so you don't need to compute this all the time. But sometimes some problems will specifically ask you to compute using this integral, so it is really nice to know this integral of the Laplace transform. But other than that, most of the time you will be provided a table for Laplace. But more importantly, when you have the table, I want you to be able to recognize forms. For example, when you take the Laplace of t to the n power, you get n factorial divided by s to the n plus 1. Well, I want you to understand that when you take the inverse Laplace, okay, of n factorial divided by s to the n plus 1, you will get t to the n. Okay, basically, when you take the inverse, you get whatever was there, which makes sense. But the important thing is when you see this form in a question somewhere, you should be able to recognize this with t to the n power. And that does take some time to build that skill. But once you are able to do that and understand the basic inverses, and that's how you will be able to solve the IVP problems with Laplace transforms and many differential equations. So some of the basic Laplaces we should know is Laplace of 1 or any kind of constant. We will have 1 over s. If you have a constant, let's say it's just 5, you will multiply with 5. So guys, when you have a constant inside Laplace, you can just take this constant out and put it outside of Laplace. So that's really useful, because at the end of the day, this is an integral, guys. This is an integral. So you can basically take the coefficient out of the integral, because that's you're totally allowed to do that. We have e to the at is equal to 1 over s minus a, and such. These are the other Laplaces. Um, and you don't need to be solving for s, because that's just some parameter we use for our solutions for the Laplace. Now let's try to solve the Laplace transform of e to the 2t. Well, our definition integral of Laplace was 0 to infinity of e to the 2t, I'm sorry, e to the minus st times f of t, and in this case, f of t will be e to the 2t dt, okay? So over here, I'm going to do a little bit of algebra and combine these exponential terms. So we will have e to the t, and we're going to add these guys together, basically. So we're going to have 2 minus s and dt, and the integral from 0 to infinity. Well, if you want to see, if you can distribute this, we will have 2t minus st, and that is the correct multiplication. And now we want to integrate this. So basically, we have a constant here, and this is e to the t. So every time you see these integrals, you can just go ahead and say 1 over 2s. This is going to be the constant part, so we're going to divide with that and multiply with e to the t 2 minus s. And this was from 0 to infinity, so basically we did integrate this, and now we're going to plug our bounds there. So e to the, what do we have here? We're going to have something large going on, so we're going to have 1 infinity so as the limit approaches to infinity, and minus, and if we have 0, we will have 1 over 2 minus s, and this infinity is usually being ignored because we want to get something convergent. We don't want a divergence. So we're gonna get rid of this infinity part. Okay, so when you try to substitute infinity into this limit will provide you with infinity, but you're gonna ignore that because you don't want divergence. And now we're gonna put a minus because we're subtracting with the second bound and get negative 1 over 2 minus s. And that's actually equal to 1 over s minus 2. Okay, so what we did find is the Laplace of e to the 2t is 1 over s minus 2. Okay, and obviously s you don't have to say this all the time, but s is greater than 2, because if you have 2 here, you're gonna get 1 over 0, which is not gonna work out. But you don't also want something negative, so you're gonna say s is greater than 2. There is a little bit longer explanation for this reason, but we're not gonna get too deep into that. And if you want to compare this result with the Laplace table, e to the 2t is under this title, Laplace of e to the at equals to 1 over s minus a. And our a in this case is just 2, so we're going to have 1 over s minus 2, just like we have down here. So we actually did the correct definition method. Now over here, we have a Laplace inverse problem. Most of the time, you will not be asked to find the inverse Laplace directly. Rather, you will most of the time solve problems involving Laplace transform, the inverse Laplace transform. So you want to be able to compute inverses when you see them. And the best way to learn these things is basically solving enough problems and memorizing the inverse transforms and the functions. So over here we have a 3 s squared over s squared plus 4. Now, when you can look at the table and try to determine what you want to do. So in this case, we're not using e to the at sine vt or e to the at cosine vt because of the shifting, they have an s minus a squared term in the denominator, and we don't have that. But rather, we do have something like sine at, where we have a constant on top and s squared plus 4, something like that on the bottom part of our fraction, on the denominator of the fraction. So if we had a sine at, the numerator and the part of this denominator, the plus 4 and the 3 must be consistent. So if you have a over s squared, and you have to have a squared. So make sure that you have the square for the numerator in the bottom part of the denominator. So most of you will say, oh, 2 squared is 4, so I have to have 2 here, which is definitely true. You do need a 2 here, and s squared plus 4. But you might say, what about this 3? Like, what happened to the 3? So in this case, we want to multiply that with 3 over 2 to keep this balance. So we're going to convert this 3 over s squared plus 4 into 3 over 2 multiply with 2 over s squared plus 4. And once you make that look like this, in here we do have something like sine of 2t. Okay, so the inverse Laplace, I'm gonna pull out that 3 over 2 there, and you will have 2 over s squared plus 4. And when you put this in the Laplace factory, inverse Laplace factory, you're gonna get, if you take a look on the table, you're gonna get sine of 2t, but don't forget your constants. You're gonna have 3 over 2 sine of 2t, and that's your inverse.